100%, something they say no natural object should be able to do.
Across the deep field of the solar system, something that should have been constant isn't. The interstellar object known as 3IATLAS has begun to drift off prediction. Its trajectory is flattening, its speed curve bending downward as if something invisible has gripped it. In the void between planets, where no drag or field exists, 3IATLAS is slowing down. So, the question now isn't where this interstellar visitor came from, it's what exactly is trying to stop it. The age problem. Among the countless trajectories charted across the night sky, one path refused to bend. The object, now catalogued as 3IATLAS, entered the solar system on a hyperbolic course, its velocity exceeding escape speed by a wide margin, its motion too straight, too certain, to belong to anything born beneath the sun. The calculations confirmed what the geometry implied. This body came from interstellar space, carrying the momentum of another system, or perhaps another era entirely. When its orbit was projected backward through galactic coordinates, the track failed to intersect with any known stellar neighborhood. Instead, it passed through a region between the Milky Way's thin and thick disks, a vast transitional zone where stellar density drops and orbits become tilted, ancient, and quiet. That emptiness raised a single conclusion. 3IATLAS had been traveling unperturbed for millions, possibly billions, of years. Nothing had deflected it, nothing had claimed it. The object's composition reinforces that sense of awe. Spectral sampling from ground-based observatories revealed a mixture of carbon-bearing volatiles and high-albedo dust, materials that should have degraded under constant cosmic exposure. Yet their signatures remained strong, suggesting that 3IATLAS spent most of its existence shielded from intense radiation, perhaps drifting in the cold outskirts of a long-dissolved system. Preservation on that scale implies formation in a chemically young environment, one poor in heavy elements but rich in pristine ices. Every parameter, its hyperbolic excess speed, its low metallicity indicators, its unaltered volatiles, aligns with an origin predating the solar system. It may represent matter condensed when the galaxy itself was still assembling, a fragment of the early interstellar medium locked in ice and dust. Now, for the briefest moment, that fragment has crossed the sun's domain, reflecting light that was never meant to touch it. There is no parent star to trace, no gravitational signature to follow. 3IATLAS moves through our system not as a visitor with a destination, but as a survivor of galactic history, an object older than the world observing it, still carrying the temperature and silence of the time before stars like ours existed. The lost star theory. When analysts extended 3IATLAS's motion backward through time, the results produced not a lineage, but a void. In every computational model, its path slid through interstellar space without intersecting the influence of any known star. 62 potential encounters were tested using Gaia's stellar motion data, yet not one trajectory produced a gravitational match strong enough to redirect an object of this velocity. The implication was unsettling. 3IATLAS had not been ejected recently from a planetary system at all. It had been adrift long enough for its point of origin to vanish from the maps of the living galaxy. That realization led to a new interpretation of its birthplace. Beyond the spiral arms, between the Milky Way's thin and thick disks, lies a transitional region where the orbits of old stars tilt out of alignment with the galactic plane. It is a sparse environment, neither part of the youthful thin disk nor fully bound to the halo, a relic zone formed when the galaxy was still coalescing. In that frontier, stellar encounters are rare, gravitational tides weak, and isolation almost eternal. An icy body released there could drift for billions of years without significant deflection, maintaining the same course until the galaxy itself turns beneath it. The kinematics of 3IATLAS support this view. Its galactic velocity is higher than the average thin disk population, but lower than typical halo objects, placing it squarely in that intermediate range. Its inclination relative to the galactic plane, combined with its chemical indicators of low metallicity, suggest it formed among the ancient stars that populate that boundary. If so, The object represents material forged when the Milky Way was still young, before successive generations of stars enriched the interstellar medium with heavier elements. In that context, 3I/ATLAS becomes less a comet and more an artifact, a frozen remnant from the formative period of the galaxy, a time capsule of early cosmic chemistry. Its untraceable path does not imply mystery for the sake of drama. It reflects genuine absence. The parent star that once held it, if it ever existed, has likely aged beyond recognition, its light diffused into the general glow of the Milky Way's oldest disk. 3I/ATLAS is what remains, the ghost of the early galaxy. If 3IA/ATLAS truly emerged from the frontier between the thin and thick disks, then its existence is more than astronomical coincidence. It is a direct sample of an older Milky Way. That region is often described as a transitional membrane in galactic evolution, where two populations of stars overlap in both age and motion. The thin disk carries the younger generations, enriched with metals and elements recycled through countless supernovae. The thick disk, older and rougher, holds stars forged in the galaxy's first chaotic billion years, when collisions with dwarf galaxies and turbulent accretion sculpted its shape. Between them lies a gravitational buffer, a quiet cold zone where debris could drift undisturbed for eons. 3I/ATLAS's path moves precisely through that liminal space. Its trajectory indicates it never shared the rotational speed of the thin disk, yet it does not carry the steep eccentricity of halo bodies either. That balance places it in a rare orbital corridor, one where ancient material could persist long after its stellar birthplace faded. The chemical hints observed from its coma align with that scenario. The ratios of carbon to oxygen, along with the unusually low inferred metallicity, match the composition expected from early galactic environments where heavy elements were still scarce. In physical terms, this means that 3I/ATLAS is built from primitive interstellar ice and dust, substances untouched by later cycles of enrichment. Its particles may contain isotopic signatures older than the Sun, perhaps older than most planets in our galaxy. The dust locked within its crust likely condensed in the first cooling waves of the Milky Way's infancy, when carbon monoxide, ammonia, and water first began binding into grains under weak starlight. As it enters our solar system, the object carries with it the temperature record of that ancient time, the coldness of molecular clouds before stars burn steadily, the faint radiation of a younger universe. No telescope can yet tell whether its inner core hides complex layering or solid stone. But the data agree on one fact: it has not been remade since it formed. It moves now as it did then, a fragment of the galaxy's early architecture, crossing the modern solar system like a ghost from a time when the Milky Way itself was still assembling its spiral arms, a comet of carbon dioxide. When 3I/ATLAS crossed into the inner reaches of the solar system, the James Webb Space Telescope was already tracking its faint infrared signature. Across wavelengths between 2 and 5 microns, its coma glowed with a pattern that defied expectation. The emission peaks did not correspond to water, the usual driver of cometary activity, but to carbon dioxide, a molecule that typically sublimates only after a comet has warmed considerably near the Sun. The ratio was extraordinary. For every molecule of water, nearly 8 of carbon dioxide were released. Such dominance of CO2 is virtually unknown among solar-borne comets. Most show the opposite proportion, where water vapor leads and carbon dioxide trails as a minor constituent. The inversion suggests a body formed under conditions far colder than the protoplanetary disk that shaped Earth. In those early galactic regions, ultraviolet radiation was weaker, stellar density lower, and chemical diversity limited. Carbon dioxide ice could condense freely, while water and methanol remained trapped within deeper layers. The spectral data revealed even more. The CO2 bands were strong, but the absence of accompanying methane lines indicated a volatile inventory distinct from that of modern comets. Its coma temperature measured barely 150 Kelvin despite proximity to sunlight that would normally drive far higher activity. The surface appeared to release gas through narrow vents rather than widespread sublimation, a behavior consistent with a dense, insulating crust that had survived unaltered since formation. This chemical fingerprint fits the object's galactic history. A body born in a low metallicity environment would have accreted simpler ices, poor in organics, but rich in oxidized carbon. That would naturally yield a CO2 heavy composition once illuminated. To the instruments aboard JWST, 3IATLAS did not resemble a typical comet warming under solar radiation. It resembled a frozen laboratory experiment from a younger cosmos. The findings reframed the question of what 3IATLAS truly is. It behaves like a comet, yet its chemistry predates any solar system pattern. Its outgassing is not random. It is structured, deliberate in geometry, as if sculpted by age and physics older than the planets themselves. In a universe defined by heat and decay, this body remains chemically precise, a reminder that some ices still remember the cold from which galaxies were born, the water paradox. Soon after the carbon dioxide spectra were released, ultraviolet instruments aboard the Swift Observatory began returning a very different signature. Around wavelength 3085 angstroms, the detectors recorded faint emission lines of hydroxyl, a byproduct of water molecules breaking apart under sunlight. The readings came when 3IATLAS was still more than 3.5 astronomical units from the Sun, a distance where most comets remain inert blocks of ice. Yet the ultraviolet glow left little doubt water was already escaping into space. The paradox was immediate. If the comet's outer layers were dominated by CO2 ice, its surface temperature should have remained far too low for water to sublimate. Models that combined the JWST data with Swift's ultraviolet flux suggested two incompatible realities. Either 3IATLAS hides internal reservoirs of water ice buried beneath a crust, porous enough to vent gas through narrow fractures, or its composition allows energy to move through it in ways not yet understood. Both possibilities defy conventional comet physics. Photometric monitoring showed that its brightness varied rhythmically every few hours, hinting at rotation-driven activity. Jets of vapor appeared to burst from localized regions, producing temporary spikes in OH emission before fading again. The average mass loss rate inferred from these events reached several hundred kilograms per second, modest by cometry standards, but remarkable for an object still in the outer solar system. The gas expanded at roughly 0.7 kilometers per second, forming a tenuous envelope thousands of kilometers wide that trailed faintly behind the nucleus. The combined evidence implies that 3IATLAS carries a layered interior, an insulating shell, rich in carbon dioxide and dust shielding deeper reservoirs of water ice that respond to subtle heating. When sunlight penetrates a vent, pressure builds rapidly, expelling gas before the surrounding crust seals again in the cold. The result is an object that breathes in slow intervals, active where no comet should be alive at all. In chemical terms, it behaves like two bodies merged into one. The exterior, ancient and oxidized. The interior, fresher, still releasing traces of primordial water. The contradiction between its frozen carbon skin and its hidden vapor core turns 3IATLAS from a relic into a living record, a body that should be silent, yet continues to whisper the chemistry of its impossible birth, cyanide, and the building blocks of life. As 3IATLAS slipped deeper into sunlight, radio receivers on Earth tuned to a narrow window of silence, the submillimeter band, where interstellar molecules announced their presence. Across the static, a single rotational line began to pulse at 265 gigahertz. The frequency belonged to hydrogen cyanide, HCN, a compound as simple as it is consequential. Each molecule carries one atom of carbon, one of nitrogen, and one of hydrogen, the same triad that threads through amino acids and the scaffolds of RNA. The signal was faint, barely a ripple above background noise, yet steady enough to map. From its strength, observers calculated a release rate near 4 × 10 to the 25th power molecules per second. In any solar-borne comet, such numbers would pass without remark. Here, they carry the weight of distance and age. It means that chemistry capable of forming life's basic ingredients does not need a planetary nursery. It can exist in the frozen debris between stars, waiting only for light to wake it. Infrared and radio spectra together painted a layered interior. Beneath the carbon dioxide crust, pockets of volatile material expand as sunlight reaches the subsurface, forcing gases through fractures that open and close with rotation. Each vent breathes cyanide into the coma, where ultraviolet photons tear it apart into CN radicals, producing a faint blue emission that drifts behind the nucleus like a trace of smoke. The ratios of HCN to water and CN to HCN fall squarely within the range seen in ordinary comets. The implication is quiet but profound. Across the galaxy, chemistry obeys the same rule. Temperature, pressure, and photon energy sculpt molecules the same way, whether under a young sun or a forgotten star in the Milky Way's outskirts. In the infrared images, that cyanide glow merges with the broader haze of dust, giving the comet's tail a pale sapphire tint that shifts with every rotation. Each particle in that plume has survived radiation storms and cosmic impacts since the dawn of stellar formation. To look at it is to see the raw alphabet of biology suspended in vacuum, letters written long before any planet learned to read them. Within 3IATLAS, the oldest ice in the galaxy still carries the potential chemistry of life, illuminated for a moment before returning to interstellar night. The polarization mystery. When light from the sun scattered through the dust of 3IATLAS, it returned with a signal